welcome back in the supreme name of Almighty Allah. So we are almost at the last lecture. Maybe we can have the last one about its summary. I mean, the whole things we have discussed in the five lectures, starting from the introduction, data models, transactions, as we discussed in the last lecture, the distributed data management system, the need and its basics we have discussed, replication, and the replication we discussed, multiple solutions, how to keep the data update, single leader, multiple leaders, and leaderless. Then we discuss sharding and consensus algorithm, facts, Lampert timestamping, and at the end we discuss the requirements and the properties of the formal requirements of the consensus, and at the end we discussed distributed transaction with two-phase commuting, which was really the core topics and concepts of the uh, distributed data management system. Last but not least, cap theorem and Paselic theorems. These are the core which they are giving the birth to the further concepts of the like application and the sharding. Okay, and there are certain types of trade-offs we have discussed. Now we are almost at the last lecture. So this lecture is about MapReduce in workflow, which is the distributing computing procedures. So we are in the distributing concepts. So as we have seen that so far, the data in softwares and all these were like distributed on a multiple network node, but the same, the computing power has been already distributed. So we are discussing the basics of the distributed computing. In the previous lessons, we talked about, as we discussed, about the distribution impacts. Okay, I mean only on storage, like to sharing the RAM, like memory or disk, and neither sharing nothing in the basics of the distributed data management. But only storage for that lecture. Okay, but here we are also discussing its computation mainly. Okay, and if the data is too much to store at a single node, it is also at the same time too much to handle and analyze at a single node. I mean, we should have to manage its workload of the computations across the multiple nodes or among the multiple nodes. In distributed computing, multiple nodes elaborate different parts of the data and communicate in communicating among each other to reach some goal. When data is too large, we discussed this thing already. I mean, for a single node, its computation is also definitely for a single node really complex to analyze. So distributed computing splits workloads across the many nodes in communicating to reach certain goals. They have some advantages and challenges in computing models birth. So if you see the challenge, the advantage is parallelism. That's a very good aspect. Inefficiency, solved last two big problems for one machine, but challenges are the concurrencies. I mean, management, internode communication. Okay, concurrency management, internode communication, and fault tolerance is really important. Like if more nodes, so we have is equal in automatically higher combined failure probability. Okay, okay, if there is a high load in the middle, certain nodes are failing. So I mean, the load on the existence nodes will be very high. So there is a fully chance of failure of the whole system. I mean, they are giving automatically the birth to automatically to the, I mean, higher complexities. Okay, or higher combined failure probability. That's very important. But computing models, so we are having actor models, MapReduce. We will discussing all these in workflow, which is data flow programming. We are starting with the MapReduce computations. Okay, it is a distributing computing model and inspired by MapReduce in functional programming originally proposed by the Google, and it's made widely available in the Apache Hadoop initially. Okay, and it's a very low level model and influential, but popularity has waned in the favors of workflow system. I mean, when workflow camp here, so its popularity is almost gone. So MapReduce pipeline is like splat, map, shuffle, and then reduce. So map and reduce in the middle, we are having two more steps of the, sorry, we have split, then mapping, then shuffle, and then reducing. So this is the main pipeline, how they are working. Okay, what does it do? Split. Split is a certain actor like master controller. So input files are dividing into chunks like 64 MB each. And map is a map worker. Each map task processes. Okay, map task processes a chunk output list of a key value pairs in we are mapping this. Okay, when the master controllers divide the input files into chunks, and the map is then making its key value pairs. In the shuffles, in the master controllers, group all key value pairs by key to shuffle them and what is required. And in the reducing worker, so the reducing worker is basically each reduced task receives key and its values produce final outputs stored to file. So this is how overall MapReduce is working. There we have multiple workers like three workers, master controller, map worker, and reduce workers. Okay, so splitting and shuffling is managed basically by the master controller, and mapping and reducing is controlling by the uh, respective workers. As we discussed, this is developed by Google initially at Hadoop architecture in fault tolerance. So MapReduce Hadoop architecture in its fault tolerance, how they are working. Okay, HDF is like Hadoop distributed file system. So they are the same like files divided into the chunks of 64 MBs, each replicated on a three nodes by default. This is how it was working. I mean, by default, this architecture is designed. So master controllers initialize and manages worker processes, and map workers and reduce workers were doing their own jobs. Master tracks their state, I mean, task state is idle and execution are completed. If you see the false failure scenario in its response, let's suppose map worker needs fail, what will be happening? So they must restart and stored locally on a failed node. Okay, and results stored on stored locally on a failed node. So for the re-execution, so master set tasks to the idle and reassign them when it's recover the map worker. So this is how the failure scenarios are managing in their response to the failure. Reduce workers fails. If let's suppose the reduced worker fails, what will be the response? This is easy as compared to the map failure, worker failure. Simple reassigns to another worker. So result stores are already on the a Hadoop distributed file system, so they will only recover from there, and the reduced worker is just assigned to another one. Okay, and this is the same for if the same reduced workers reconstruct or recover again. Okay, and this is quite safe. Results are stored already. Master controller, this is quite difficult scenario. If the master's failing, so it means that we are entire computation must be restarted. I mean, like it is the difficult scenario if the master controller is failing. Okay, there are certain examples of the map reduce. Okay, word count, how they are working. So they are splitting the document, okay, into the chunks, sequence of words. Then they are mapping for each word like W in they are emitting. So W1 in O or D the same, and they are becoming its key value pair. And the reduce worker is making its output final W11 okay, M, and they are returning WM. So where W is a word and M is holding the keys. And the same examples for the matrix vectors multiplication. I can multiply V, but here the matrix multiplication, the vector is basically in the memory, fits in memory. Okay, so the same starting with the split as we have seen from the start, they are basically working to split, then map, shuffle, and reduce workers, but maybe sometimes shufflings are missed in the middle. Okay, so if you see that the map for each cell Mij, okay, reads V from memory and emit them the Imij multiplication by Vj, so they are becoming the key value pair. And reduce worker is nothing but they are returning the ixi, where I is equals to the summations of uh, mk multiplication of vk. So this is a little bit advanced examples of understanding how they are working on the memory, how they are working the computations of the Hadoop. Okay, how the Hadoop architecture works, and it's how it's fault tolerant. Okay, we discuss here the failure and its response, and this is the how Hadoop architectures are working. But we see that the MapReduce has been banned in favor of the workflow system. So, I mean, Hadoop architecture is now replaced with the Spark architecture almost. Okay, now we are switching. We are not discussing more the matrix by matrix multiplication, which is nothing. A is a matrix n by n, and its multiplication with p mx p o m multiply p. So it is a multi-step a little bit. So map would happen one time, then reduce, then again mapping, and then reducing. But it's a complex example, really. Uh, but this is more like high level stuff. We will just understand about its core stuff, how they are working. So after the MapReduce, which is, I mean, already banned by the workflow of systems of the Spark, Apache Spark. So this is like quite common, okay? I mean, if you see here the MapReduce, we discussed here already influentially, but popularity has waned in favors of the workflow system. So now, like Hadoop architecture or Apache Hadoop is not that much usable, but people are using Apache Spark. Okay, in why? Because that is waned by the influential popularity of the workflow and its benefits they are associated with. So MapReduce is a too low level, okay, for iterative algorithms or complex operation compositions. In when it was on a very low level, but workflow systems allows general DAGs, so directed acyclic graphs of operation, which is a little bit higher version. So example of these are the TensorFlow, PyTorch, like for deep learning, okay, which we are using in nowadays. Apache Tez, so which is again for low level DAGs. It is really helping, but it is back going like more relevant to the back MapReduce. So Apache Spark, it is a general using for general analytics. Okay. So last, if we see what is Apache Spark. Apache Spark is a workflow system designed for data analytics in parallel in distributed settings. So this is quite common using nowadays. And let's quickly compare Spark versus Hadoop, like Hadoop architecture versus Apache Spark architecture. So we have feature in Hadoop MapReduce in Apache Spark. So this is a quick comparison. Okay, the primary language Hadoop MapReduce is using Java. In Apache Spark is using Scala, Java, Python, PySpark. Okay, so all of them they are supporting the multiple languages and algorithm structures. So the Hadoop's MapReduce is a sequence map and reduce steps. Okay, they are working on a MapReduce inspired from the map and reduce, okay, in functional programming. And Apache Spark is working on a general DAGs of operations, directed acyclic group of operations, and intermediate data written to Hadoop distributed file system in disk. But in Apache Spark, which is the main feature in comparisons to the Hadoop MapReduce, they are keeping in memory, but memory as in comparisons to disk is much faster. So we can see them, they are keeping in JVM, Java Virtual Machine, okay? And they are much faster. So primary data structure, as we discussed already in the Apache Spark, is using for general analytics. So for analytical, we need more computation. So that's why they are running in the memory. So primary data structures. So files are divided in chunks, like we discussed already in 64 MBs, and divided on 3 different nodes. Okay, they call them HDFS blocks, Hadoop distributed file system blocks. In Apache Sparks, we are basically using RDD, resilient distributed data sets and fault tolerance. It is re-execution or failed task. Okay, so this is how the response to the failure of the map failure, like reduce worker failure or the master controller failure. But in the Apache Sparks, we are using lineage. Okay, reply operations from a log. We are generating a log here or developing a log. So from where we are failing, so we are recovering from the log. Evaluation is eager and Apache Spark is lazy. Defer until actions. Okay. Heavy level query. Hadoop MapReduce is none, but high level queries using by the Apache Spark, which is Spark SQL, with the catalyst of the optimizer, which is quite optimized also. Okay, so we are almost at the last of the lecture. Okay, what is resilient distributed data sets? So which we discussed, that is the primary data structure of the Apache Spark. It's important to discuss. Okay, it is a general distributed data sets, but it's also complex at the same time. General distributed data sets that can hold semi-structured data. Okay, any semi-structured data of any type. Two types of operations they are performing, like transformation. An input RDT is given and they are generating RDD, but lazy in actions. In another one is a RDD, but they are providing a values or output. Okay, but it's trigger action execution. I mean, they are different until the action we discussed above already. This is the evaluation, how they are working. So key Spark concepts, as we are discussing the Apache Spark in the workflow system. So we need to understand about these concepts. And the first one is lazy evaluation of RDD in lineage of RDD. So lineage is nothing but it is a fault tolerance of the Apache Spark. Okay, but understanding is important then. Lazy evaluation is Spark does not immediately apply transformation. Okay, we have seen the lazy, it is deferred until the actions. Okay, so execution is deferred until an action is triggered. So what is the benefit? They are avoiding unnecessary temporary files, enables a query optimizer. Okay, and this is the benefits and advantages of the lazy evaluations of RDD. So this is one of the important concepts in the Spark workflow. Okay, in the workflow systems under the Apache Spark. Okay, the second concepts we are discussing lineage of RTD. Okay, lineage strategy is okay. The lineage Spark strategy is to achieve resilience. Okay, as a temporary RTDs are not stored here. Okay, and however, the Spark keeps a persisted logs of the other of the operations performed. Okay, we have seen that in the Apache log, we discussed that the failure tolerance is basically we are replay operations from the log. So that is actually lineage. Okay, in lineage is basically keeping the persistence logs of the operations performed on it, so which allows the recovering the processed resilient distributed data in case of failure. So I mean, the instead of storing the intermediates RDD, Spark keeps the persistent log of all transformations. So applied the lineage graph if a partition is lost due to the failure. So it's instructions by reapplying the lineage. No need to store all the intermediate data. So these are the two important concepts in the Apache Spark Apache Spark workflow system, which is nowadays mostly using. Last but not least, and Spark provides collections of predefined transformations in actions that can be used out of the box. Okay, so they are providing some sort of actions. Okay, the first one is map. Okay, it is a transformation type. Okay, apply f as a function to each element, so which producing a new resilient data set, distributed data set. Flatten map, so it's the transformation apply f to each element, flatten results, so they are producing one new RDD. In filter map transformations, keep all the elements where predicate p is true. predicate is a constraint, and last reduce. So if we remember, this almost working the same but a little bit different. In the map reduce, it was like a split, map, shuffle, and reduce. So I mean, Spark is providing here a collections of predefined transformations and actions here. But here we are starting with the map. In the middle we have flat in filtered, and at the end we are reducing. In reducing is a basically an action, the first transformation. So apply f repeatedly to pairs until one value remains, okay, and that is the output, but nothing. Last but not least, the high level Sparks APIs, application programming interfaces. I mean, the APIs we are using, it's for the workflow system, it is data frames, it is table like structures, okay, table like structures similar to pandas or data frames. Pandas prefer data frames, most common Spark interface nowadays, and support SQL application as well. And the data set strongly typed versions of our data frames. In dataset is another API of the high level Spark APIs of version 2.0, and it's mainly used in the Java in Scala. And last but not least, which is really important for this Spark SQL, so the SQL interface for RDDs and data frames. So on an SQL interface, we are developing resilient distributed data sets and its data frames. Okay, and it also includes, we already discussed that they include the catalyst for the cure optimizer for efficiency. If you see here, when we were comparing the both of them, high level query, okay, in the Hadoop MapReduce, in the Apache Spark, which Apache Spark is nothing but it is a workflow system, uh, uh, which is now the competitor of, or already the winner or influencer in popularity and against of the Hadoop MapReduce. So they are using the Spark SQL with the Catalyst optimizer. I mean, the queries are here very optimized in comparisons to the Hadoop MapReduce. So that was a quite quick introduction. You can call them the about the distributed competitions of what is MapReduce and what is workflow system. So hopefully you will like it, and possibly we will cover some of the quick references, summary tables of the his whole lectures. Okay, and where we discussing the physical data structures at glance. Okay, and these were the data structures we studied in the data models, physical data models like a hash table, B-trees, LSM tree, and Bloom filter. And we are using best cases, read, write, and persistence and range queries. Okay, and all these things, replication approaches in at glance. Okay, if you remember from the replication approaches in the distributed data management, which was single leader, multiple leader, and leaderless. And we also discussed in the transactions about